Hello, everybody. I'm Jordi Baylina. I'm the technical lead at Polygon zkEVM. And today I want to talk very much about Polygon 2.0, mainly what's the plans for Polygon for the upcoming month. And I think it's very interesting because mainly what we are doing is scaling Ethereum, going in the path to scale Ethereum. So what's Polygon 2.0? I like to think about Polygon 2.0 as a constellation of rollups. So we have right now one rollup, is the Polygon zkEVM. But here in this constellation of rollups, we expect other chains to be here. Here, for example, is going to be other public networks like Maiden that we are constructing there. We are going to, well, at least we are going to propose to port or to move Polygon POS to a Polygon, so to a rollup. So the people that's building in Polygon POS will have not only the POS, but will also have the security of Ethereum on top of that. And it's going to be also some private chains or semi-public chains. So any kind of chain, no matter what the properties they have. And this will bring a constellation of rollups. Okay. So why constellation? Well, the main topic at the end here is to have many chains, but that they interoperate one each other, that there is composability between one each other, so that you can communicate, transfer information, but not only transfer information, also transfer value between one chain and the other. And this should be so fast. We are thinking here that this composability should be in the order of seconds, maybe 1 minute, in the 1 minute, the order of very few seconds, this composability. And all this is because the zk technology. And more explicitly, I mean, we are talking about the revolution of the zk, but more explicitly, there is one breakthrough that's actually what enables all this, and is the recursion. Well, right now with Starks, it's really easy to do recursion. That means that it's easy to pack two proofs in a single proof. So you can build this kind of Merkle, so it's not Merkle trees, but would be trees of proofs. So with a single proof, actually, you are proving many proofs. And this is the idea. So it's going to be a single proof that will prove all the chains. So it will aggregate all the proofs of all the chains. And this proof will act as a clock. And every time that the proof is set there, you know that the state of each chain is valid, is correct, and you can do a transfer of information and value in between that. Okay? So this composability is really important. And important is, so this zk is what gives mainly the security. So all the chains will have the same proof, because this is what guarantees that the states evolves in the right way, and there is no single chain that's cheating, even if it's a private chain, because at the end, this is proved by this validity proof. So no wrong transactions, nothing can be cheated. Everything is secured by the zk and by the circuit that's proving the zk. That's mainly the rules of Ethereum that are running in each chain. One of the biggest concerns about the L2 is the liquidity, the diversity, like the sparse liquidity that the liquidity gets in many chains, and this reduces the value of the whole ecosystem. And this has been a concern for the community in the last years, I would say. With this system, the idea is that we solve somehow that, because it's going to be a single bridge, if you want, a single place where all the value is going to be a shared liquidity between all of them, so that when you are transferring from one chain to the other, the only thing that you are doing is just updating the database, updating where each of these funds is at this point. Okay, so this solves the shared liquidity This solves the problem of the liquidity in layer 2s in this constellation. And this, again, this is possible because the zero knowledge, because the proof, the zk proof, that guarantees that in the bridge, I mean, only the coin can be only in one chain or in the other. Okay, and you cannot do like double spending, and the chains cannot cheat. As I mentioned before, we are aggregating proofs, okay? And you can imagine that's going to be different provers for each of the chains, and at the end, these proofs needs to be aggregated and then committed to the L1. All this process of decentralizing the chain is going to be run in a specific consensus layer, and it's going to be coordinated in this consensus layer between different actors, between different provers. So anybody that wants to build a proof or want to collaborate to build this proof will be able to collaborate in this aggregation and this coordination chain for the proof. Yeah. The other point that's important here is that it can be a diversity of rollups. As I mentioned, can be public or private, but they can also have different consensus. Maybe there are some private chains that make sense that there is a centralized sequencer, some public chains that are going to be decentralized with a fully decentralized sequencer. Some of the chains will have data availability on L1. Some of them will become like validiums that will be that's going to be just so that the data is not going to be in L1. So each chain will be kind of autonomous, but they will guarantee the security because they will be EVMs, and they will guarantee that that what they are executing is valid and correct. I like here to put an example of to see the powerful of this, and imagine a private chain that's kind of can be even private, where there are some internal transactions, but at some point wants to interact with some public chain, maybe by sending some funds or by doing some exchange to some exchanges to some DEX, or I mean just two private chains that they are coordinating and they are sending information through these rollups, or public to private. I mean, all the possibilities between public and private chains that with these shared systems and with this composability in 30 seconds, I think this is an important step for scaling and for scaling Ethereum. Yeah. So, and all this is the idea is that internally, and this is a little bit more internal, but the idea is that we are building a single stack. We call it a single zk stack, where it's going to be, of course, it's going to run on top of Polygon, but it's going to be a single prover, a single prover with a single, let's say, EVM system that gives the security, with a single client, a single bridge. So the idea is to have a single full stack where everything is coordinated, and so everything is integrated. So this is a little bit the summary of the Polygon 2.0. This is what we are going to build. I mean, a lot of news will happen in the upcoming month because we are working really hard on that. But right now, I would like to give a update of the current state of the, of the Polygon zkEVM. You know, right now, as you know, Polygon zkEVM is the only EVM equivalent rollup that's running right now in mainnet. We launched that on March. We are onboarding a lot of applications. We don't care very much about the airdrops, TVLs. We care about developers, that the applications, that they have a low friction between them, so that the developers should feel that they are developing, they are deploying the things like in Ethereum. The only thing that they should be cheaper and faster, but they should not notice any difference. They should not use any specific tooling, no specific compilers, no specific debuggers, no specific tools for that. When we are scaling Ethereum, you should deploy as if you are part of Ethereum. Okay, and this is where we're working really hard in the team in fine-tuning things, finding edge cases and putting everything together. And I think that we are getting to a point of stability that where I would say that the applications quite comfortable in deploying them, so that they don't see any difference in deploying in one chain or the other. Okay. So what are the next things? Well, there is one thing that we are working really hard, and we have been working. I mean, we have been working really hard in improving the performance of the prover, but we're also right now working very much in working the performance of the remaining pieces. I would say is the client, the sequencer, the database. Because at the end of the day, if you want to scale, it's not enough with scaling the prover. You need to scale all the pieces. If you want to execute thousands of transactions per second, you need a database that supports thousands of transactions per second. You need RPCs that support thousands of transactions per second. You need, you need to synchronize fast enough to support all these transactions. So working in all these pieces is really important, and this is one of the core, one of the most important pieces that we are focused on. The next one is we are also improving the provers. The prover, as I told you, we want to generate these proofs really fast. Right now, proving 10 million gas batch, it takes about a minute in a big computer. Okay, this is good. I think this is for a EVM, for a single zkEVM is good, but we want to improve also that very much. And for that, one of the things is we are working with BADCOPs. This is variable degree composite proofs. The idea here is that what we have is that right now what we have is a kind of a monolithic proof. It's a proof is in a single proof, we can do many things. We have many resources. For example, in the single proof, we can do like something like 2,500 ketchucks. We can do arithmetic operations. We can do binary operations. We have certain amount of RAM. We have different resources, and this is fixed, and this is limited. Okay, so we cannot, in this proof, we cannot put more than that. But if we put less than that, we are wasting part of this proof. So the idea is we have a new mechanism where using this idea of recursion, where we can, instead of having like a big monolithic proof, we can have like subproofs that they are computed in parallel, and we can scale a lot. That means, for example, if we are not using a lot of arithmetic operations, we can have a smaller proof, so we can go faster. But not only that, if for example, we have a lot of binary operations. What we can do is we can aggregate. We can have many proof of binary applications. We can aggregate all of them, and we can aggregate as many as we want, and then composite this proof in a single proof that have everything together. So this gives us a lot of performance. And we believe that this we can speed up, I don't know, 3x, 4x, 5x the speed of generating proof and the capacity that this proof will contain. Okay? So this is one topic of research, well, topic of actually working hard for that. The other thing that we are working is in the PIL2. Actually, as you know, we were using a language for writing all the arithmetization for writing the arithmetization for the zkEVM. This has been given us a very, very, very good results. This idea of allowing us to separate the different layers, the arithmetization layer, the ROM layer, the cryptographic layer in different teams, different pieces with different teams, is what allow us to go fast in the going to market idea. But this also, for example, for auditing has been very, very useful because, for example, we were able to have different teams with different skills to audit different pieces of the system. Okay, and one of the pieces is the arithmetization. We need to, we are tagging. We are working really hard on this new language because we need it for the BADCOPs. We need a language to use in the BADCOPs, but we are using also this update to do many other things, like programming, for example, putting the constants, all the constants in the same language. Right now, we're different scripts that, they were separated files, so we can put them together in the same file. And also it's another important thing is that this is going to be a language that's going to be more programmatic. I mean, we can, for example, have 4 whiles. So instead of having, right now, for example, what we have is we have like separate scripts that generate spill. Okay, so the idea is instead of having these things, we can do the same thing in pill. So this will allow us to just have the single pill for the definition of the verifier. Okay. Well, a lot of advantages, and you will hear a lot about this in the next weeks. Okay. What else? This is from the functionality perspective. What we are working really hard right now is data compression. As you know, the biggest limitation on the biggest limitation right now in the rollups is not the prover. I mean, the prover scales as much as you want. I mean, if you have more load in the network, you just spin up more provers. If the load of the network grows, you just stop provers, and you can scale as much as you can. The biggest problem or the biggest part of the price of an L2 transactions goes to the data availability. So in order to improve the data availability, there is like 2 things. Okay, one is the one that's working in the Ethereum Foundation very much, is the EIP 4844, and dank sharding and all this. This will, EIP 4844, for example, will increase about 10x the capacity of the data availability in L1. So this is good news, and this will happen really soon. We're working really hard to implement and to use this EIP. But the other thing is data compression. I mean, if you can put a transaction that takes 100 bytes in, you can put it in 10 bytes, then you get a winning of 5x or 10x. So how you compress a transaction? Well, compression you can understand. I mean, as a set of commands where you can. I mean, for example, you have one command that's just put this information as a raw transaction, but you can have different compression. One thing, for example, that you can do is compress the value. Instead of using, I mean, 16 digits of the value, maybe you can use a kind of a floating point kind. So you can have a mantissa, an exponent, and this, for example, you can compress this thing. So you can have a command that says, okay, compress this value. But the important part of the transactions, so what are the parts that gives you more that are more difficult to compress? Well, the first thing is signatures. I mean, the signatures is not necessary to include the signatures in the data availability. Instead, what we can do is include a proof that, if you have 100 transactions, you can include a proof that these signatures exist. Okay, so and this can be compressed a lot. So if you have 100 transactions, you can you have something. I mean, you can get a compression. So this data availability. So the data availability of the signatures can be reduced to a constant size per batch, and this is really low. And this is one of the things that can compress a lot. The other thing that's difficult to compress is the addresses. I mean, one address have a very high entropy in general. It's a random number, comes from a hash. Okay, so probably the first time that you are using an address, you will have to publish the full address. But the idea here is that you have a state of the transactions and the addresses that you have used before. So in the data compression, instead of referring to a given address, you can refer to an index, to some sort of database of the address that you have been using. Okay? So, and when you put all together, these are very conservative numbers. You can get a 5x. Compression. Actually, in the last, the last results, this is more a 6, 7x than a 5x. But 5x is it's a conservative measure here. This depends very much on the kind of transactions and so on. What means that when you are putting on top, when you are joining this data compression together with the EIP 4844, we can get easily a 50x scalability, and this will happen in the upcoming months. The idea is that when the EIP 4844 we should be able to process 50x what we have right now. That's already 2-3 Ethereums, more or less, what we have at this point. So this is the plans. This is what we are working hard, and Yeah, thank you very much, and I'm here open for questions. Have plenty of time. Any question?
You mentioned in your talk that Polygon POS was going to become a rollup. Is that because they announced it was a Validium? Is that an officially new position, or is that?
We announced a Validium, but I can tell you that the idea is that when danksharding is ready, we will put the data on chain. This is what I would love to happen.
Okay, great, thanks.
Thank you for hello. Thank you for your talk, Jordi. I'm just wondering, like, you spent a lot of time thinking about how to scale. You must have some dreams or kind of ambitions for, like, what's the coolest use case that you're thinking of? Like, would you mind sharing?
The use cases for scaling.
Well, the use cases for all of what you do.
I mean, I think that I think what I'm thinking, and this is very much the way I'm thinking, is even all the transactions, everything that the humans do, they hold some sort of value. Even when we talk each other on when, of course, there are some of these transactions that holds higher value, some of these transactions that holds lower value. Okay, so for me, it's that this value is committed, is used in the blockchains. This gives a lot of fairness, a lot of transparency, and this helps a lot. But it's not only about humans. Here is there is a full topic, for example, where it can grow is the transactions between bots or between I mean intelligent robots, or Internet of Things can. I mean the things can interact with each other. So there is a lot of interactions, a lot of operations. Of course, at the end, it's a matter of what's the offer. It's an economic thing. It's what's the price, what's the offer, and measure this long tail of transactions that can happen is probably difficult to measure. But what's clear is that there is a lot of demand. And I believe this is very much like when internet. I mean, at the beginning of internet is what's the limit of the bandwidth that the routers have. I mean, you just can grow the bandwidth and it will be filled somehow. This is the way I'm thinking, and probably here we are thinking in transactions that are more money related with the money. I mean, DeFi and these things. This is probably because they are. First, you see the value clearly. There you can measure very easily, but there is a lot of other transactions. I mean, for example, voting systems on the governance systems, for decision taking, for scrolls, or even for communications. I mean, when you say something in Twitter, it would be good to prove, for example, that you said something like that. So there is a bunch of applications, a lot of transactions that if you have these common good, I mean, where you can make these transactions in a very cheap manner, there is plenty of space and plenty of applications that can run on that. But we need this to be, I mean, the low cost, and of course, secure, scale. I mean, all what we are building right now. Technology is not ready yet, and we are growing, and we are improving this technology to reach these stages, and this is somehow where we are going to.
Hi.
Hello.
Can you hear me? Yeah, perfect. Quick question. You mentioned that the proving time is currently around 1 minute. Where do you think the proving time could potentially be in 2 years, 3 years, 5 years?
I think more than 4 or 5 years. I think that the proving time with this, just with these bad cops in the few months, I think we can be in the order of seconds. Thinking about 20, 30 seconds is definitively valid. The other thing is that with these bad cops right now, right now we're doing 10 million gas. We could do it 1 million gas, and that would be great for most of the applications. Why we are doing 10 million gas? Because we are not, because we are processing, so we want to fit at least one transaction inside. We don't want to split. There is some techniques to split the transaction like in different batches, and you can do the things. But if thinking in a batch, you want to have at least the minimum batch so that you can fit a transaction. And 10 million gas is, I mean, doing a transaction of more than 10 million gas is I would say, it's not practical in general, so that's why 10 million gas. But with these bad cops, it's perfectly possible to do batches of maybe 1 million gas or 500K gas. So, and then these transactions can be generated much faster. I mean, maybe you can generate a proof with, I mean, maybe with 5-10 seconds on that. And maybe there are rollups that wants this kind of finality. Okay, so this is perfectly possible. Another thing is, for example, the aggregation. You know, when you have different proof and you want to aggregate, more or less aggregating two proofs after generated, it's more or less about 1 second. The order needs 1 second. So this gives you the order of magnitude of we have right now. It's a lot of development that's happening. I mean, there are new cryptographic systems that are being investigated. I know, for example, Ethereum Foundation is investigating a lot all these NOVA with aggregation things. We need to see if this is better or not, if it works or not, but it could be really revolutionary. Another thing is the hardware acceleration. Here we have a little bit disappointment in working in hardware acceleration because we see that the CPUs are really fast, and also here the kind of proving system we are using is a little bit memory intensive, and for hardware acceleration doesn't work well. But there are other proving systems and there are other innovations, and I don't have a crystal ball, but this is going really, really fast, and thinking in proofs in few seconds is perfectly, I would bet that this will happen, and not even 5 years, I would say even less. Yep. So thank you very much. This is all. Any question, you can reach me.